Thanks everybody to come. So I worked with the Choose team for the last 6 months on the live build engine and Projucer. And first of all, I want to thank the team for all the valuable input and contributions to that. That was really helpful. Let's start with a little statistical investigation. Who of you has heard about the Projucer C++ live build engine before? So that's most of the people. That's great, because then we can keep the demo very short. Who has actually used it or at least tried it out? That's a few. Okay. And who of you used the live build engine on Windows already? It's just one. Okay. Just saying here, we just released 4.3 last week, and it has a lot of improvements, and it also has a free-to-use license for a yet-to-be-defined period of time. So just grab it from the download and try it out. You don't need a commercial license for Choose. Okay, let's see what we have. I split the talk into 2 parts. One conceptual part with a little demo how the whole thing works and what it means to use C++ in a live coding environment. And the second part will be a technical thing about linking when it comes to live builds versus static builds. Let's first have a look at the demo. We have the Projucer here, and when we start it up, we can see it's this typical, you know that. You can manage your projects here, and you can browse source code files. And here we have the live build engine that will hopefully start in a second. Here, yeah. So it compiled your source code and just starts up the JIT engine. And when we click on this little play button here, it will invoke this constructor and show us a nice instance of our code here. So that's a running instance. We can interact with it. We can do all kinds of stuff with it. And one nice thing is that we have literals in our program. For example, color definitions like here. We can modify those values, and they will update in real time in the running instance. That's a little sugar on top, but what usually happens when we change our source code is that the engine detects that it needs to recompile our source code, relink it, and execute it again. So let's imagine we're used to US writing, and we misspelled the set color thing here. The engine detected that we have a problem. It could not actually compile the thing. We can click here, see the problem. We can fix it, and it will recompile and re-instantiate our live executable. So that's the basic thing that you should know about to follow the talk. The main purpose of the whole thing is to minimize the edit compile test cycle so that you can see the effects of your changes immediately in a running instance. This is especially valuable for UI design, DSP prototyping, and all kinds of other things. If you want to know more about this, you should see the talk from Vlad Vojna just in this room after the lunch break. He will present some real-world use cases for that technology. So let's have a short look on how the whole thing works. Let's assume we have 2 source code translation units in C++. And what we do is either we compile them directly, or we load the already compiled version from the disk cache, and this is loaded to a in-memory object file. Afterwards, when all object files are compiled, we can link them together into a in-memory executable, and this is finalized, and as soon as this is done, we switch the memory from read-write to executable and can call into this code from the live build engine. That's the basic principle. So what happens when we change our source code now? So we change source code translation unit to source code translation unit dash. This will compile a in-memory object file dash. It will link it into our executable. And at this point, we replace all the symbols or the addresses of our symbols in the symbol table of the executable by the new one. So all calls that go to the old one before now go to our new binary we just linked in. So basically, the old object is removed. After that, we can call again into the executable, and we see our live instance updating. So in principle, that's not such a big thing. Sounds pretty simple, the concept, but the trouble comes in when we want to use C++ in this context as a source code language. And that's why I want to compare C++ to a invented, constructed language that we just built for live coding. So imagine we had this language, which features would it have, and how does that compare to C++? There's actually languages like this around. One example is Chuck, and this is a on-the-fly audio programming language from Stanford. Has anyone heard about Chuck? Oh, that's pretty many. Okay, who actually used this for something useful? Okay, that's 2 people. Good to know. We'll come back to this later. So the first thing I would do in the ideal language is to guarantee crash freeness, because crashes overcomplicate a lot of things. So I would design the language as a declarative or functional language probably. But when we look at C++, this is imperative, and it's inherently not crash safe. We cannot do anything about the programmer dereferencing a null pointer or something like that. And that's the reason why the Projucer live code engine runs in a separate process. So if it crashes, you can just restart the whole thing without losing your changes in the project files or something. Second property, I would use some kind of unified runtime environment. That's pretty useful because we could restrict the programmer to a certain subset of functionality that the OS offers, and we could design the subset to be safe. So the programmer had not all arbitrary access to all functionality, but that's not the case in C++. C++ says there should be no language beneath C++ except assembler. And this means we need to handle a lot of quirks from all our supported platforms manually ourselves. And there's a long list of things that come into here. So there's different object file formats. There's a non-standardized ABI, and there's a lot of problems with that. So for example, name mangling is very different on the various platforms. Unix is pretty reasonable, but when we look at the Microsoft mangling, it's just I don't know, ridiculous. And the Clang implementation tries to mimic that behavior, but at some points, if you look at the code, there will be comments like this saying we don't even know how to mangle their types anyway. So when you come here, I don't know what happens. So the takeaway point here is if you ever want to mangle for the Windows API, don't do it on yourself. That's just a lot of work. That's not useful. But that's not everything. So there's exception handling that's different on all the different platforms, and calling conventions. We had to mangle. We had to support the DLL import calling convention edition on Windows manually, and RTTI works completely different on different platforms. Another thing is intrinsics for extended instruction sets. So what we do here, we ship the Clang intrinsics headers for our specific version of Clang with the Projucer. So you always have the right ones available, because your system specified ones may not fit what Clang expects there. Another property would be, I would optimize for simplicity, uniformity, portability, and all these kinds of things. But C++ optimizes for efficiency. We only want to pay for what we use, and we are platform agnostic about that. We want to pay for what we use only on our platform. We don't want to pay for something that is restricted on another platform. And this encourages compiler vendors to implement system-specific optimizations for performance reasons. The consequence of that is that headers and implementations are compiler and platform specific. And that's why when you run the Projucer, you need to have these things available on your system. So you need this specific version of Microsoft Visual Studio to run it on Windows and Xcode on Mac. I would also design it to have strong static typing, because this would probably allow for runtime restoration of our state. This means when we have our live instance and we recompile a part of it and re-instantiate it, it could continue where the old one stopped. But this is unfortunately probably not at all possible with C++, because we allow explicit violations of the type system. And the consequence is there's no runtime state restoration in the Projucer. There's actually one point pro C++, and it turns out to be exceedingly important. And that's what we see here. Our ideal language is something that probably will never be used in real-world use cases. And C++ turns out to be used by a lot of people today and for a very long time to come, I think. And we saw that with Chuck. So Chuck exists and does exactly that, but people just don't use it. So it doesn't really make sense to, or it does make sense to work on it, but it won't have the biggest effect. So all these quirks make it really hard to build a live build engine that's based on C++. But hard is not impossible. And I think all it needs is some really good tools. And the Projucer live build engine is a tool, but obviously we are using other tools. We are using LLVM and Clang. LLVM is a compiler infrastructure, so you can build compilers that use the LLVM tools and libraries. And Clang is a C language frontend, so it compiles C, C++, and Objective-C with the LLVM libraries. We use a lot of those libraries in the Projucer that you see here, and there's one interesting thing that I want to go into here. It's that we use the Clang AST not only for compilation, but also for calling into our executable. And this has exactly the reason that mangling is pretty hard when you want to do it on Windows. The Clang AST library has the mangling implementation for Windows from Clang, and we use this to call into our C++ executable, because there the mangled symbols are in the symbol table, obviously. There's still be dragons. LLVM and Clang are moving targets. There's a lot of commits all the time, and maintenance costs can be really enormous. So whenever you want to do something similar and do custom modifications on Clang or LLVM, be sure to watch a video like this before, or see that you can keep your modifications really minimal, because you will spend a lot of time otherwise to rebase to new versions of your libraries. Just as a little overview, compared to the choose library, what's the lines of code? I know that lines of code literally don't say anything about the complexity of our project or anything else, but it's kind of a rough indicator when it comes to the question, how long will it take to find the line that causes our bug? And we had the situation, we had a bug when we tried to port the live build engine to Windows, and the symptom was that when we instantiated a live component, it immediately crashed, always. And there was one assertion failing in the runtime dynamic loader, which you can see here, and it was not directly obvious what the problem was, but we will see this in the end of the talk. Before we can go into details about this, I would like to revision some details about linking. So let's imagine again we have two source code translation units, one foo, one bar. One of them defines a function bar, the other one calls it. Both include the header. When we compile the bar C++ now to an object file, it has one symbol in there, and it is a so-called defined external symbol, which means the object file, or when linking the whole thing, the linker expects to find this wrong. This means that the object file provides this symbol in the translation unit. When we compile the other one, we have one defined symbol and one undefined symbol, and here it's the case that the undefined symbol must be available in some other object file. The interesting point here is that the displacements of our functions is 0 in the object files. And that's probably not really intuitive because we defined a function, but it somehow has no address or no displacement in our object file. The reason is that this is exactly the point that why we have linkers. We want to compile our translation units in isolation so that when we change the source code for one translation unit, we only want to recompile that single translation unit, relink everything, and be done. If we didn't have this, we would need to recompile everything every time, all the time. So going forward from here, we have the two object files. The linker will combine them, will resolve all the symbols, and it will exactly fill out those missing pieces here. And this is what we call relocation resolution. And this is pretty important for the technical details that we'll see in a second. Doing that on Windows, we'll see our crazy mangled symbols again, and it's pretty difficult to look into the executable. There's a lot of stuff there. I cannot go into detail about this so much. The interesting thing here is that Clang generates us 32-bit relocations, and we'll see what effect this has just in a minute. So looking at the assembly that we would have for our two functions, it's like that. The foo generates a stack frame with the first push and the move. The second move moves our value into a register, then it calls our function bar. Afterwards, the pop will destroy our stack frame and it will return. When we now link it to the other one, it will replace the call by the actual address or the actual offset to this function. And we can jump into it, return done. And this is the case when we compile and link without position-independent code. The concept of position-independent code is very interesting. There's some literature in the end that you can read more about it. The only thing that I want to mention here is that they use a little trick to simplify some load time relocations. And the trick is that we don't resolve our function call to the actual target. We resolve it to a little relocation stub. That's also sometimes called function stub or trampoline. And this one will forward our call to the actual target function. And we will use it later and see why is that a good idea. Just if you want to try out this on your own, there is something like an as-if rule for linkers. So if the linker sees the opportunity not to create those stubs, it can also avoid doing that. So don't wonder what's the problem here. I don't have a relocation stub. Especially for small examples, this will happen, that you don't have relocation stubs. So back to our problem. We had this bug, and I thought, what would be the best approach to get more information about that? And the first idea was, okay, let's take the object files and link them statically, and maybe that gives us some more information what the problem here is. And so we compile it, we resolve relocations here, and at load time, when we put the executable into virtual address space, we resolve some more dynamic relocations. Depends on how we use position-independent code. The difference here is when we compile, when we build at runtime, this load phase gets split up, one part to the compile phase and one part to the link phase. The compile phase will compile to in-memory translation units, so we don't actually need to load them anymore. And at link time, we can just resolve all relocations in one go. And this has some interesting side effect. that was exactly the point where we had our bug. So imagine what does the static linker? It will load all our object files from disk into virtual memory, and it would put the object files next to each other in the virtual address space. Because if you leave spaces in between, your executable will grow bigger, and no one wants bigger executables without any reason. The difference for us in live builds is that we allocate the memory for our object files just like we allocate all other memory. So we will have probably, for example, address space randomization. And this is pretty interesting. By the way, we need this. We couldn't do the static build because, as we saw, when we change the source code, we want to replace one of the object files, and we don't want to load them all again and link them all again. We just want to link this one additional object file. So in this case, we replace this one by that one. And the consequence of this is, and that's the reason why it was not really useful to link statically to solve our problem, was that those relocations will typically stay within the 32-bit range. And the interesting thing I found when I tried this out is I used the same object files linked statically, and it worked perfectly. And I thought, what's the problem here? What am I missing? And what I was missing was exactly this point, that when we do our runtime compilation, this will easily exceed the 32-bit range, and the relocation offset will not be sufficient to call the function in the other object file. It's just too far away, literally. So how can we fix that? Let's take the trick from the position-independent code, and what we have here is this 32-bit relocation that Clang compiled for us, and we cannot do anything about this. This is already prepared. We could change all the implementation of Clang or the object writer or all the implementation of the runtime dynamic loader, but as we saw, we don't want to make too many changes in our libraries because this will increase the maintenance cost a lot. So we just solved that by redoing the trick. And we add another relocation step that is now a 64-bit relocation, and we forward our original relocation to that one and add the new one to be resolved later. And this jump now actually, it can go to the other object file because it has all the 64 bits, and it can do all the long jumps. If you're interested in the patch, we have this online, and we hope to be able to contribute it back at some point. It needs to some testing still, but the great thing here is as soon as I implemented this change, we never had a problem with this particular issue again. So it's really, really stable. And the other point is that the adjustments we need to do to realize that were really small, so we don't have problems when we go to further new versions of LLVM. If you want to know more about this, there's two great articles by Eli Bendersky. He writes a lot about compilers and linkers, and these are really interesting low-level, under-the-hood articles about how the whole thing works on the example of the ELF format. And yeah, the Microsoft documentation is not really good, but if you have time, then you probably figure it. So that's all of my talk. Thanks for your attention.